Hello and welcome to this 10th and final part of this series of videos introducing the mathematics of signals. For a list of all the videos, please click the link on the top right of the screen. In this part we're going to look at approximating a Fourier transform with a Fourier series computed using an FFT, a fast Fourier transform. This sounds like a right mouthful and a bit of a bad idea, but this is essentially what we end up having to do in practice. So let's just talk through it and try and understand all the implications of that. This talk builds on all the other ones, so if you haven't watched those, in particular if you haven't watched part 9, then you should go and do that first. So just a quick outline. We've seen that the FFT, the fast Fourier transform algorithm, implements Fourier series, not a transform as the name might suggest. It's from a continuous signal perspective, it's implementing Fourier series, which assumes signals are periodic. Here we're going to try and answer questions such as what happens when this meets real world signals that are non-periodic or have periodicity different to that assumed by the FFT. This is basically going to always be the case. You might have an analyzer computing a fast Fourier transform, it'll have some assumed time period, and whatever you're measuring will pretty much never ever match exactly the period of the time analyzer, because even if they say they are, the clocks will be slightly different. So what solutions can we use to deal with the issues that might arise from this? So as we've said, we'll often use the FFT to approximately compute a Fourier transform. The Fourier transform is what we usually want in real life. It's the thing that actually tells us what frequencies in a real world signal, because it's not locked to this certain periodicity and set of harmonic frequencies in the way that Fourier series and the FFT are. But the FFT actually computes a Fourier series, albeit on a sampled version of XT. And potentially there could be problems with this sampling, but that isn't usually the problem actually, so long as the sampling frequency is high enough and the audio capture hardware is working properly. I say that there's a huge area of DSP and audio system design to kind of make sure that that does work, but in practice engineers sort those things out very well, so actually it doesn't tend to cause an awful lot of trouble. The problems that we need to understand occur because of the difference between the Fourier transform and Fourier series. And let's start off just by looking at an example. So imagine we've got some signal XT is sine of 2 pi ft, so this is time harmonic with frequency f, and things are straightforward if f exactly matches one of the harmonic frequencies fn of the Fourier series that the FFT is computing. But what happens if it doesn't? Well, let's look at an example where it does. First of all, if you put in the frequency and that matches exactly a bin frequency here, 1 kilohertz is a bin frequency, then you get exactly that little nice clean spike just at that frequency. Great signal to noise ratio from the algorithm here, not seeing anything going on at all. We're just seeing that frequency that we wanted come out. But what happens if we shift just a tiny bit to 1001 Hertz, which isn't a bin frequency? Well, now we see this, which is that we've still got the peak in the right place, but we've got loads of energy turning up in all sorts of other frequencies, even frequencies miles away from 1 kilohertz, so down to 0 hertz up to 2k. You know, we're sort of like about 60 or 70 dB down, but it's not insignificant. There's an awful lot of kind of like spectral smudging going on. This energy from that one frequency is kind of ended up in loads of other frequencies, which is really not what we want, quite frankly. We're going to find that our estimate of the spectrum is really badly biased, because whatever frequencies you put in will just turn up all over the place. So first of all, let's just try and see why that might be happening. And if you have a frequency that doesn't quite match the periodicity being assumed, then what you effectively have is you have one period of the signal come along, up 0 to t, and then you just kind of, the Fourier series will just kind of assume that you're just starting that again, because it's assuming the signal is periodic. So even though it wasn't periodic, we'll assume it is, and that means we get these funny little things that happened at t, where we might get kind of discontinuities in the signal, jumps, we might get changes in derivative, generally kind of horrible stuff that you can't approximate very easily with smooth functions like sines and causes. But we're going to try to, and much like we did with things like the saw wave or the square wave in one of the earlier videos, we're going to see how we might try and fit this. And I've got a little animation just to show that, but rather than just build up these frequencies from low to high, I'm going to start with the most significant ones first and then kind of work down in order of reducing significance. So the frequency we've put in here is a more exaggerated example than the graph at 1 kilohertz in the last slide. But the frequency we've put in is between the 4th and 5th harmonic. So you can see immediately in the spectra at the bottom, those are sort of hooked up the most, but the others are all doing something quite significant as well. And we're going to see 4 and 5 come in first, and then we'll go in order of kind of decreasing significance. So let's put in 4 and 5. Even though those two doesn't match very well, and then we start to add more and more, doing them in order of reducing significance. And you start to see that we have to go quite a long way down that list. You have to have quite a lot of frequencies in here, in this case 16 in this animation, and then we begin to get fairly close to the behaviour that this actually had. So to beginning to capture both the smooth behaviour in between the discontinuity and also not a bad estimate around the discontinuity either. Let's just watch that again. So the first thing that comes in doesn't match. Second one comes in, okay, begin to get something, but it takes quite a long time to converge and really smooth out. We've got to have a lot of other frequencies come in and contribute at different levels, different amplitudes and phases as well, to match this frequency that doesn't fit to the set that the Fourier series is trying to do. So that is essentially what's going on and why we need all those frequencies, and why we get this kind of spectral smudging. So let's try and work out mathematically what we might do about that. And to understand this a bit better, let's just look at the two equations. I'm only looking at the forward transform because I'm only performing kind of analysis here. I'm trying to get from a time domain signal to a spectra. And by comparing the two, we know that they're quite similar. The main difference is that a Fourier transform analyses all of the signal from t, from the Big Bang till all the way in the future. Whereas the Fourier series only analyses part of the signal from minus t over 2 to plus t over 2. There's a scaling in there as well, but otherwise they're pretty similar. And we can say that actually this is equivalent to a Fourier transform if we assume that the signal xt has been multiplied by this window function wt, which is defined to be 1 from minus t over 2 to plus t over 2 and 0 otherwise. And if you take that and you plonk it into both these things, well, with the Fourier series it kind of does nothing because it's 1 throughout all the range, minus t over 2 to plus t over 2, so you can just sort of get rid of it. And actually what you find is that this approximate version, xn on the left with a little tilde on top, which is just indicating that a window has been applied, is actually the same. So it makes no difference to the Fourier series at all. What it does in the Fourier transform is it truncates the range of integration. So this now ends up looking rather like a Fourier series test integral without the 1 over t, but an important difference is that f isn't fn, so f could be any frequency, not just a harmonic frequency. So this kind of thing at the top, this idea that actually what we're doing is, when you're doing a Fourier series, is taking the Fourier transform as something that's been windowed into just that time period, is going to be really useful. So if you're using a Fourier series or FFT to estimate, to approximate a Fourier transform, what you're doing is windowing the time domain signal. So the equivalent signal we've Fourier transformed is xt times wt multiplied by this window. And the question is, what does that mean for the modified spectra with the window, x with a little tilde on top, versus the correct value just for xt? And to understand that, we're going to have to take a little slight diversion into something that I considered whether to include in this lecture series earlier and didn't, but I'm now going to have to do it because it's required for this explanation. So a little aside, we've been thinking about these systems where you put in a signal x, it passes through the signal and you get an output signal y, and we've talked about the fact that the response of a system can be a transfer function h, and that y is really neatly represented as just x times h, so they're just multiplied, and that's one of the reasons that transfer functions and complex numbers for representing spectra are really useful. But we know that this is actually equivalent of a time domain signal, time domain system where you put in a signal xt, get out a signal yt, and these are all related by Fourier transform here. So the question is, how is the response of the system related to the transfer function? What we got in the time domain? And the answer is we have something called ht, which is again related by Fourier transform to big HF, and this is the impulse response. And this is something that in acoustics and audio people are normally quite familiar with, because if you go into a room and you want to understand the reverb in the room, obviously that affects everything that's in the room, but the easiest way to hear exactly what it's doing is to go in and clap to produce a really short excitation, and that makes the reverb really obvious. But actually mathematically it works like that as well. It actually tells us how that information in the impulse response, in the response to the clap, or to get something louder, maybe a balloon burst or a starting pistol shot is what people might use to measure these things. That actually is enough information mathematically to reconstruct y from x. And we know that because that's what the frequency domain things told us. You know, we have a statement in the frequency domain to get us from x to y via h, so it follows that we must have a time domain one as well. And that time domain statement is something called convolution, which people use sometimes slightly different symbols for. I've used this little cross in a circle. And let's just take a minute to understand what that is. So here's a graph where we've got a signal on the left, an input signal, which in this case is a kick drum, and then we have our impulse response of the space, and then finally we put those two together by convolution, and the reverb gets applied to the kick drum, and we get something where the kick drum sounds like it's in the space. And visually, if you compare the xt and yt, you can see that xt's kind of been smudged out and it's now got some of the kind of smudgy characteristic of ht applied to it as well in yt. And if you have a few hits, then the impulse response applies to all of them, so we get smudging of all of these things. Or if we have a more complicated signal, then you'll get them all smudged all over one another. So the general message here is convolution. You know, if you want to think what it does, it kind of represents perhaps something like reverberation quite nicely. But mathematically what it's doing to these graphs is it's smudging them. And our impulse response was causal. It only goes into positive time, which means it only smudges to the right. But if you had something where it had values for negative time as well, or negative values, it might not be time that we're smudging with respect to, then you get smudging in both directions. And they use this in image processing for blurring. So let's go back to our time versus frequency domain, and let's just collect all those relations over here. So we'll just take those two relations like that. And we've seen that multiplication in the frequency domain is convolution in the time domain. But that's not what we've got in this windowing problem. We've got multiplication in the time domain. We've got this new version of this signal. It's the original signal multiplied by a window. So you can kind of see that all these things would Fourier transform to their own Fourier transforms. But the question is, how are they related? What should the question mark be? And if you compare the forward and reverse Fourier transforms, this sort of gives us a clue, because these statements are almost the same. All we've done is we've swapped f and t, and we've got a minus sign in the exponent, but other than that they're exactly the same. So there's obviously a kind of symmetry at play here. We saw this when we talked about how these were developed. There's a kind of sort of cycle and symmetry. And what that means is, perhaps surprisingly, that, you know, if you multiply in the time domain, what you actually get is convolution in the frequency domain. So the Fourier transform of multiplication is convolution, and vice versa. So when we apply this window in the time domain, what we're going to get is smudging in the frequency domain by the spectra of the window. So it makes sense to look at the spectra of this window, because that's going to tell us how much the signal that we want to analyse is going to get smudged. So let's just go back to our previous slide where we were up to. What's that mean for XD, little tilde, the windowed version, versus the spectra without the window in? Well, the version with the window, with the tilde, is going to be the version without the window in, smudged, convolved, smudged with the spectra of the window. So what is the spectra of the window? Well, our window function was this. It's something that just pops up to 1 between values minus t over 2 and plus big T over 2, and it's 0 otherwise. Sometimes gets called a top hat or a boxcar function, or a rectangular window as I've called it here. And the Fourier transform is just the integral of that. That's just plugging in the Fourier transform definition. Of course, you can actually limit those integration limits to minus t over 2 to plus t over 2. And this is quite an easy integral to do. It's one that you might like to try yourself. And the result is well known. It's something called a sinc function. And this looks like this. It has a peak at 0, so it's going to smudge, but it's going to keep the frequencies centered around the frequency that they should have been. So we saw that in the original graph, but it's going to smudge them out to other frequencies as well. And so it kind of attenuates, so it's going to smudge less and less as you get further from the main peak, but it is still going to do something. But weirdly, this doesn't actually affect Fourier series. Fourier series actually, for the set of harmonic frequencies you put in, work perfectly. So why is that effective smudging not affected Fourier series? And the reason is that if you center this exactly for a frequency driven on a bin frequency, so I've not said exactly what these frequencies are at the bottom here, but the grid lines are going to be bin frequencies. So if you put an input frequency on a bin frequency and then you smudge it, what you will get is this kind of symmetrical smudging like this. And it just so happens that all the frequencies the Fourier series are looking at, except for the input frequency one, all happen to be 0 on the sinc function. So you smudge with this, but actually it gives a perfect result of no smudging because it only has a value that's non-zero at the input frequency. But what about when we move the input frequency slightly to the right? Well, what we're going to get then is this, and suddenly it's all a lot more visible. Suddenly, if you put in a frequency that doesn't match one of the harmonic frequencies of the Fourier series, suddenly it can see this smudging. And you can see that we're getting lots and lots of non-zero values coming up in the output of the Fourier series. They're attenuating away from peak frequency, but they're still definitely there. And that is the reason for this smudging that we saw on this graph. Because this was computed with a FFT and therefore Fourier series, that this line, the orange line decaying away, giving all this kind of smudging to nearby frequencies, all this spectral leakage, as we call it, is due to this sinc function being a little bit offset. So the question then becomes, could we choose a better windowing function that would do this less? And the answer is yes, we can. And there's various different choices, but a popular one is a Hannin window, this orange line here, which is sometimes called a raised cosine or a cosine squared function. I've written it in the sort of raised cosine term here, so it's a half plus half of a cosine one period, and you just kind of pick it so that it joins up nicely at the ends to give something that is continuous and also continuous in its first derivative, so it's smooth where it joins the parts of the window where it's 0. And this is really useful because what it's going to do is it's going to kind of fade in and out the signal xt when we multiply. And that means that even if xt wasn't periodic, it's going to get faded in and out in a periodic way such that it's forced to be smooth and effectively periodic. So it's going to mean that the Fourier series has a much easier job when trying to approximate xt. And if we look at the spectrum of that, which is the smearing functions, we've seen what's important, we can see that we get a wider though lower main lobe, and then but very quickly get to 0 at the sides. So you can actually look at the main values of here. So the sinc function has a value at t, as we know. We've got a value at t over 2 and two values at t over 4 at the neighbouring frequencies. And those are just directly related, first of all, to the half at the start of the definition of WT. So much like the sinc function came from the rectangular window, there was 1 from minus t over 2 to plus t over 2. We've got a half here, just lifting that cosine function up by half. So that's where the value of t over 2 in the window function at the centre frequency comes from. But then the cosine in the definition of the window can also split down into two complex exponentials, at plus or minus f delta f, and they give t over 4, so that's where these t over 4s come from. But we can see that away from the peak it's reduced a lot faster. And if you want to use a Fourier series, so a Hanning window with a Fourier series, you'd see very little benefit. In fact, actually it would make it worse, because what it's done is spoilt the nice orthogonality property of the frequencies. We get some smudging, so actually we've got a wider main lobe. So, okay, you know, the frequency's been brought down to t over 2 rather than t, but that's easy enough to compensate for. It's the two values at the neighbouring frequencies that are a bit more problematic. We've kind of smudged it out a little bit. So if you had something that was going to Fourier series, work with the Fourier series nicely, there's no point in having a window. It's just going to smudge a bit. But if you actually got something that isn't periodic, then actually it's going to improve things quite drastically, because if we shift things a little bit to the right, we put in a frequency that's not really, doesn't match the assumed periodicity of the Fourier series, then we can see that we get some values around the peak still, but the orange line, the Hanning window, has gone down to pretty much nothing within a couple of FFT bins, whereas the sink function arising from the rectangular window, i.e. no window in, is smearing energy quite widely. And this is nicely seen on a log frequency scale. We've got level relative to centre frequency in dB on the left here, and then we've got sort of log frequency relative to the sort of offset relative to the centre frequency, but then on a log scale normalised to delta f on the left. So the centre frequency plus delta f is at 1, plus 2 delta f is at 2, etc. And the sink function has a null at that first offset. The Hanning doesn't. That's because of these two half values just at the two neighbouring bits on two neighbouring bins on each side. But then after that, it attenuates an awful lot faster than the rectangle window does. So we get about 20 dB a decade with a rectangular window, and we get about 60 dB decade attenuating our spectral smudging with a Hanning window. So finally, and just to put it all together, let's just think how we might compensate for that attenuation. The Hanning window, when we multiplied by it, you know, it wasn't all 1. It turned the signal down. It attenuated the signal, and we saw that the peak value was at half the value that it was for the sink function. So how do we compensate for that? Well, here's our Fourier transform of xt wt, and we know that that is going to be equal to the actual Fourier transform of x convolved, smudged with the Fourier transform of the window. Now, if we accept that a little bit of smudging is going to happen, the main problem is that it's been attenuated, it's been dropped down. So smudging sort of accepted, we need to recognise that attenuation, and that attenuation is actually by something I call W0 here, because it's like the 0th term in the Fourier series of W. It's the mean value of W. So if you look at W and you work that out, what is the mean value? Well, for a rectangular window that's 1 all the way from minus t over 2 to plus t over 2, it's just 1. But for a Hanning window that rises up from nothing to 1 and then back again, it's a half. So it's thrown away half the amplitude. So that is why we would see this reduced. We need to compensate for that. So we've got that factor there of a half, which we can work out quite easily. For different types of windows, as I say, there's other types of windows other than Hanning windows. This would be different, but for a Hanning window it is a half. And then we look at what we might compute, which is a Fourier series of xt wt. And this is this that we've seen before, and just the relation relating those two before that we saw in the last lecture. And finally, down the bottom, we have the thing that we would actually compute, which is the discrete Fourier transform of the sampled version of xt, which is xk. And here we've also got a sampled version of the window wk. So we can take that and we can work out xn tilde. And finally, at the top of this chain, we have the Fourier transform of xt, which is the thing we actually wanted to estimate, so no window in here. And what we're trying to do is kind of start from xt in the time domain, go digital, Fourier transform it, and then go up through these various sort of conversions to get to the Fourier transform xt, the something that represents the signal that we heard in the real world. So we can do that. We can sample it. We can do an FFT. We can go through these scalings, and what happens is that first of all you kind of turn around the equation on the second row and say that, well, xd is going to be xd with a little tilde, the windowed version, divided now by this W0 factor, the mean value of the window. And then we've also just got to compensate for the fact that that's a density, whereas Fourier series push out amplitudes, and the way we do that is multiplying by t from the data from the Fourier series. So we can actually get xn from the FFT, and then we can get xd evaluated at fn by this conversion here. So just to summarise, because there's quite a lot of equations on that slide, the first step is that we sample the signal xt to get the discrete version xk. We multiply xk by a sampled window function wk. Then we take the FFT to get xn with the window in there, and then we multiply by t, the period of the Fourier series, divided by W0, the average, the mean value of the window, to get xd, the amplitude density of x sampled at fn with minimal artifacts. And just to close the loop, we can see here that if we do the original experiment again, but with a Hanning window in there, you can see that with the right W0 in there, we still get the right peak value. There's a little bit of peak widening, but it's fairly minimal. But what we get is much lower spectral smudging. That green line is at least twice, nearly 3 times as low as the orange line in terms of dB. So that spectral smudging is colossally reduced. So windowing has helped us approximate a Fourier transform with a Fourier series computed using an FFT. So to wrap this up, a Fourier series can be used to estimate a Fourier transform, but the finite time period it observes causes spectral smudging. Mathematically, this is convolution with the Fourier transform of the temporal, in time domain, windowing function that has been implicitly implied. So a rectangular window has been implicitly applied if you just used a FFT or a Fourier series instead of a Fourier transform. But deliberately windowing with a function that tapers towards the end of the observed period, such as a Hanning window, can reduce the artifacts of this. But we need to be careful to compensate for the energy it removes. And that is the end of this series of lectures. So I hope that you found these useful. In many ways we've looked at some quite difficult topics. In other ways we've only just scratched the surface. This is where, if you're not already studying with us, some of our courses can help if you want to look more at this, or there are other resources around online if you really care about digital signal processing and want to dig in. But I hope this has been useful without getting too much into the digital signal processing, just to give people who have to use things like frequency analyzers an idea of what's actually going on under the hood and understand some of the settings that you might see, such as windowing and FFT lengths and things, and make good choices and really understand what they're doing. So I hope that you found this beneficial.